Hey everybody, you already know who this is. It's your boy Laz, and we're going to be doing the next part of our exploration of laboratory software here. Today we're specifically going to be looking into classification, which I know I've touched base on, just with the Atterbergs and the grain size analysis or sieve analysis. The test with many names and whatnot. Unfortunately for this video, this one isn't going to be streamed. There's just something going on with Telegram. I'm not too sure what is happening per se, but yeah, so that's just how this is going to be. I do want to kind of overall say for this video, it's going to be a lot more me talking and explaining things and actually showing the program. We are still going to see the program in action. We've already seen that in bits and parts from the data entry that has been done already. But yeah, anyways, enough of that. Let's log in, man. Let's make some magic happen. All I ever do is talk, right? That, no, and well, actually I can exit out of that. Okay, so let's talk about classification systems. We're only going to be looking at two specific ones that are used more common in my industry, and that's going to be the unified class system and the AASHTO based classification system, which I know I have talked about before, off and on, or in great lengths and details. So for that, I have both the charts that we're going to be referencing for today. Well, that I'm going to go over mostly for how this program is going to work. So when you have a soil or rock, aggregate, however, whatever type of earthwork-like material, I guess is the best way to put this, goes through this classification system. And the idea of classifying your materials is so you know what group it goes into. Only because for job specs and whatnot, it might call for specific soil types and or classes to be utilized for the intended use on the job site, which that's what all these codes down here are at the bottom, which I'm going to explain it as we go through it. So at least for the unified class system, it pretty much works like a flow chart and whatnot. So as we start and whatnot, you're going to make a visual examination of the soil to determine whether it's highly organic or coarse-grained or fine-grained. Borderline class is determined through the amount passing to 200. So this is kind of your first part. If you think that it's organic-y, then you're going to perform an organic content. That's what this side box is over here. So before I even skip around and jump around some more, I do just want to say, so usually the best common practice is if somebody needs a classification done in general on soils, you typically want to do a wash, a sieve analysis, Atterberg limits, and an organic content if it calls for it. And in most cases, if people really want that, they'll usually just request for all of that. But technically for the unified class system, as we see as we go down, your most important thing is a wash and an Atterberg to determine if it falls into any of these classes and whatnot. You can do a sieve analysis, but really it's just determining what do you have from how much rock or gravel do you have compared to sand. So let's continue through the chart, and we're going to start mostly on this side. So we would do our wash, which that's what our first step would be. And after when we do our wash, we have to determine, do we have 50% or more retained on the 200 or 50% more that is past the 200. So this is just indicating how much material passed your number 200 sieve, and then you can kind of go from there. So if we have less than 50%, then it would be coarse grained material. Then you would run a sieve analysis, which is, like I said, for a sieve analysis, it's pretty much for this, you would just need to determine your fraction of number 4 material. That's all your sieve analysis is. You can do a full sieve analysis like how I demonstrated in the last video if you wanted to, which would give you a much more specific, better value. But at least for the unified class system, this is all that you would need to do. And then when you run your sieve analysis for here, you have to determine if it's going to be gravel or sand, which if we look right here, if your gravel is greater than sand, then we're going to stick to our gravel. Or if our sand's greater than our gravel, then we're going to stick with sand. And all that's determined on our number 4 sieve. So if we move on down to the gravel and whatnot, now it's asking, okay, how much passed your number 200 sieve? So remember, here at the start, if we have 50% or more retained on a number 200, we'd go over here. So let's say, for an example, if we had 45% passing the number 200 sieve, we would still come to this side first, regardless. So after that, we have to figure out, okay, how much did pass through the number 200? So if we have less than 5% passing to 200, then we would continue to here. Where then from here, when we do our sieve analysis, we can get values for CC and CU from our grain size graph and whatnot, which this is more covered in the actual classification ASTM. I think it's I know it's D24. I think it's D2487. Don't quote me on that. I mean, you can Google it, Unified Classification System, and it'll tell you the ASTM number. But in that specific specification, it'll tell you, depending on what values you get, which these you get from performing a full sieve analysis, will give you those values. And then from there, you can figure out if it's well graded or poorly graded, which that's fully from doing a full sieve analysis. Now, I will say, and just like how I covered, it does say run a sieve analysis initially, but just like what I said, technically you're really determining how much fraction that you have on your number 4 sieve. So if you only do the most basic part of this whole thing, technically you can't say if it's well graded. You can only say that it's well graded unless you do a full sieve analysis on it. So if you do have gravel, which I can tell you, if you're usually testing gravel in general, you're usually going to do a full sieve analysis. Typically that's what people do. They're usually not only concerned about how much is passing to 200 for when it comes to gravel. So even though I'm saying that in general, in all honesty, you would be able to tell which one is which. But if you only did just, hey, we have this gravel sand mix, and we just want to know generally how much gravel is in here, then really you just only have to sieve it over a number 4 and then see however much is retained on it. And if you have more gravel than sand, which usually means if you have 50% or greater, then you can call it gravel. But might I regress, about, I'd say 90% of the times, if you're testing anything that is considered gravel, you're usually doing a full sieve analysis anyway. A wash is kind of hit or miss depending on the intended use and what it's going to be for. But depending on that sieve analysis will determine if it's well graded and poorly graded, which I'm going to cover that once when we do get to the program and whatnot, and demonstrate that, because I do have a pretty good example that's going to show that. Give me 1 minute. Okay, sorry for that pause, people. My my cat wants to keep coming in and out. Okay. Anyways, let's continue on with this. So, depending on your 200, it's going to depend where you're going to start. So, if it is 5% or less, which means exactly what it is. So, if you have 5.1%, then it's not 5%. Then you would move to the middle one, which you have between 5 to 12%. If you have 12.1%, then you would move on to this last portion, which is anything more than 12% passing to 200. So if we kind of go back to my earlier example where I said, okay, we had 45% passing to 200, boom, we would go right to this point right here to determine what that would be if it's gravel. So that's if we had 200% passing, or not 200%, 45% passing to number 200 sieve, and if we have 50%, well, greater than 50% of gravel, which is material greater than our number 4 sieve, so that's 4.75 millimeters. Big is your size of your rock. Then this is where we would start here on the whole flow chart. So depending with that, then we just follow through just how it shows, kind of like how we did with the 5% or less passing. If we were between the 5 to 12%, then we just have to inquire a dual symbol. So this is indicating if it's GW, GP, like GW, GM, GP, GM, GW, GC, and GP, GC, which I'm going to kind of talk about these symbols and whatnot as we continue. Really, ultimately at the end and whatnot. So if we have more than 12% passing, then we're going to run an LLPL on the minus 40 fraction. So the LLPL means that's pretty much your Atterberg limits. Your LL is your liquid limit and your PL is your plastic limit. And usually when you do that, you test it on material that's less than number 40. On your number 40 sieve. So then you do that, you run your Atterberg limits, and depending on how it plots is going to depend where it's going to go for your classification. So if it's below your A line of your hatch zone, then on your plasticity chart it'll be a GM. If the limits plot in the zone, then it's GM, GC, and then if it's above the A line in the zones, it's GC. So let me open the program real quick, and we'll take a look at the Atterberg just to see. Let's see here. Atterberg limits. Perfect. Man, this thing's going to be weird, aren't you? Yeah, sorry, I had to adjust the screen size so we can actually see everything that's going on here. So this is your plasticity chart. This here is what they call your A line and whatnot. So when they're talking about, hey, where it plots depending on how plastic it is, this is what they're talking about here. Depending on where this dot lands depends on how it's going to be classified in the end and whatnot. So, and for your liquid limit versus your plastic index, all that's just calculated by what your liquid limit's going to be and what your plastic limit, or no, your liquid limit and your plastic index on what that's going to be. And in order to get your plastic index, it's your liquid limit minus your plastic limit gets you your plastic index, or your PI as they'd like to call it. So down here, this chart here, this is what's actually that's actually going to be your liquid limit, and then your y-axis over here, that's going to be your plastic index, or your PI. So that's why it plots there. But that's what they're talking about when it comes to. Oh geez, yeah, it opens up everything, doesn't it? I don't have to print everything. Just want to quit. Okay, is it just going to behave now? This is weird. I don't know why it's doing all this. No, you don't save nothing. Or maybe I should pay attention to that. Okay, so that's what this is talking about here. So if we go over to this side, if it's sands, I'm pretty sure if you've been paying attention, it's following the exact same premise as what the gravel is. The only difference is just your codes have changed. So unlike before, we had GW, GP, or GW, GM, or GW, or GP, GM, GW, GC, and then GP, GC, and whatnot. As you can see, it's almost the same thing here, but instead of the G's, now it's replaced with S's, which G pretty much just stands that it's gravel, and then S just indicates that it's sand. But it's following the exact same premise again. So even if we start with the same premise that I said before, if we had 45% passing, our 200 sieve, and we did our air quote sieve analysis, in other words, determine what is passing the number 4. And obviously, if we have a high amount that passes a number 4, so let's say if we had 90% that pass a number 4, then it's going to be classified as a sand, which is going to start with S, and then it just follows this exact same procedure. So if we had more than 50, or if we had 50% or more, which in my example I said 45, it would automatically go to here to the 12%, and then depending on where it would plot here would depend on where that's going to be with your Atterberg limits. Now I can tell you, usually when it comes to sands and gravel, they're usually not plastic. So usually you'll have silts in it, and usually if it has a lot of silts and whatnot, that's what's going to make it go past your 12% mark. So take a sip of tea here. Okay, so let's say we have more than 50% passing. Okay. Excuse me. So kind of like how this is considered coarse grade, now this is considered fine grained material. So if it's more than 50%, you should always run your Atterberg limits. So you're going to run an LLPL, which is your liquid limit plastic limit, on material passing your number 4 sieve. And then from there, it depends on where your liquid limit is going to be at. If you have a liquid limit that is less than 50, that's going to be your low liquid limit. If it's going to be greater than 50, then you're going to have a high liquid limit. And then it all is based upon where it's going to plot on on your chart for when you do it. But if we look here, if it's below the A line, or if you have a plastic index of that is less than 4, then you should determine if it's organic or inorganic. So the thing is usually with soils that have organics in it, even if they're considered plastic, it's usually going to have a low plastic index of some sort, or plot it low on your chart that I showed before. So from that, they really want you to focus on, does it appear to be organic or inorganic, which the way to tell for that is color and or odor. So usually for organic material, it's black in color, really dark browns. It's a very, very dark color, which is an indicator, but generally it's the odor itself. So it's going to have an organic smell, like decaying plants and whatnot. it usually doesn't smell pleasant at all. So, with that, if you do have something like that, then that would classify as an OL for this. If it's inorganic, then you would say it's ML. If you have limits that's plot in the hatched area on the plasticity chart, which I kind of forgot to show that. So what's considered your hatch area. Let's open this up again. Wow, this thing's just going to be weird. Of course, doesn't want to show everything on the screen. No, I did that. But anyways, this area here is considered your hatch area. So there you go. Okay, cool. I can minimize that. And then, of course, if it's above the A line and you have a plastic index that's greater than 7, then you can say it's CL. If you have a high liquid limit, then is it below the A line or is it above the A line? And then depending from there, if it's organic or not, you'll be your OH or your MH, or it'll be CH if it's above your plasticity chart. So to kind of go over all these codes here, this ultimately in the end is how a soil is classified. After going through this whole procedure, it's going to fall in one of these categories. So if you kind of picked up on it already, you see GW, GP, and you see well graded and poorly graded. It pretty much just means for this here, you have gravel that's well graded or gravel that's poorly graded. When you have the in-between symbols, as you can see, we have, GW, GM, or GP, GM, so it's saying that it's gravel that's well graded or gravel that's poorly graded. And then we have our GM here or our GC here, which indicates when it's the in-between, where does it fall along the portion of our Atterberg limit. Now, you might be thinking, okay, but wait a minute, Laz. So if it's between 5 to 12%, it doesn't indicate that you have to do an Atterberg limit. And you're correct. You don't have to do an Atterberg limit if you have fines that's that low, but you have to be able to classify it along the lines. If you think if it is going to be plastic, do you think it's going to be either below or above the A line, or is it going to be well, actually no, if it's either going to be below the A line or within the hatch zone. That's right, because it would be, oh yeah, never mind, GC's on there. Yeah, so it would have to fall within one of these other ones, and that's why you have the option of indicating that if you want to. So that there is just an experience thing that you develop over time and whatnot, determining what silts or clays, if you think it's going to be above or below the hatch line. The in-between mark is always a tough one to figure out, but usually with gravel, you're just dealing with silts, and if it's silts, it's usually below your A line or within your hatched zone. So usually, if you do have something that's between 5 to 12% for your gravel, it's either silts, probably just dust when it comes to gravel, honestly, more so than anything. But so usually it's going to either classify as a GWGM or a GPGM. But all that's based on actually doing a full sieve analysis. You can't, by default, if you do not perform a full sieve analysis on your material itself, you can't determine that it's well graded. So that means you have to assume automatically that it's poorly graded. You have to prove if it's well graded. Okay, that's the only catch when it comes to classifying things. You can't, you know, because most of the time your material is usually poorly graded anyway. If it's coming from a pit or something, or the pit, the ground, or anything like that, it's usually poorly graded. It's just naturally occurring material that is there. So, well graded material is material that has been manipulated and engineered in a way for it to become well graded. So things like asphalt and concrete, which it's kind of me repeating myself because this is the thing that I kind of talked about in the sieve analysis. But this is a more in-depth talk about classifications and whatnot, so we can actually see the system working. And we'll go back to this and check this. And it's like I said, I have a few examples so we can check to show the ease of having a laboratory program auto-classify for you. Because back in the day, you get all this data and it's like, okay, well, where is it at? Is it here? Is it there? And then you have to call the shots. Okay, is it here? Is it there? And whatnot. Unlike for a program, it's just going to do it for you automatically. And then, of course, we have our GM and our GC, which just indicates where is it at along your, for doing Atterberg limits and whatnot. I can tell you, you can have material that's more than 12% passing and it be non-plastic. And if it's that, then it's just going to default as a GM because it's going to be below your A line, because it can't even show up on the graph because it's non-plastic. You can't determine liquid limits or plastic limits, so you can't get a plastic index. So that's how the default for that usually works. Even though I'm talking about gravel is the same as sand if you look. So here we got SW, SP, SP, SM, SW, SM, SWSC, SPSC. And that's, if it's between our 5 to 12, we got our SM, our SMSC, and then our SC. So as you can see, it's following the exact same thing, and the only difference here is instead of G's, now we're S's, which indicates sands. So as we get into our fine graded material, which is silts to plastics, good lord, silts and clays. Good lord. I'm losing my mind here. So with our silts to clays, which this is kind of following the exact same mantra, where our silts are usually going to have a low liquid limit, and then our clays are going to have a high liquid limit, because clays can hold a lot of moisture. Because remember, back in the first video for Atterberg limits, everything is just a moisture content to get the values that we need for the test. So silts can't hold as much moisture as a clay can. So that's why if you have a low liquid limit, then it's going to start here. Where here you have, OL and ML, which this just indicates if it's organic or not. You have your ML, CL, which it's just inside your hatch zone, which that's just defaulting as if it's inorganic. Now, if you're inside the hatch zone and if it is considered organic, you can do OLCL technically. So that is a changeable symbol. It usually just defaults to that, because if something's organic like peat, kind of like how it covers here, because peat is covered as PT. So that's what's in these brackets, even though it's really hard to see that being a T, but it's technically a T. So usually if it's peat, it's people don't want to use that. You really don't want to build on anything like that. So usually if something's classified as peat, it's very rare that they would want to know all the properties about it unless they plan on using it for construction material, either as a construction material or even for geotechnical, if they're planning on installing like piles or something to bypass the peat and whatnot, to figure out, okay, well, whatever structure that or whatever type of material the pile is going to be made out of, would this affect that material? Where if it's a steel or concrete, or even if it's like stone columns or something like that, how would that affect that? It's only then is when they would care about doing the full suite of testing where it would fall somewhere in between here. But most of the time, if it's for new construction, or they only want to use suitable materials. If they see peat, it's just an automatic, okay, it's got to get removed or something, you know. Usually it's removal is what they typically do. So that's why this is kind of up here in the first step off to the side, because it's such an unsuitable material that, hey, if it's highly organic soils, you should determine that now, instead of later. Because technically, to determine if it's highly organic, you only have to do an organic content. So you don't even have to do a wash and all this other stuff. You can just do an organic content, and depending on what the organic content's going to be is where it's going to depend if it's peat or not. Usually it's if it's 50% or greater, they consider it as peat. But every single engineer in our organization is a little bit different for what they call organic, which I'll probably cover that a little bit more when I cover both the classification systems. Because remember, this is only the unified. We still have a whole nother one to cover here, but I think the other one's going to be a little bit easier, though, when we get to the AASHTO. So that's the other thing to kind of keep in mind there, for at least if it's anything greater than 50% passing to 200, and you did an organic content, and let's say it's considered organic. So let's say we had like 55% for organic content tests and whatnot, and we did the full suite of testing, but the limits plot in the hatch area or whatever, well, instead of saying MLCL, you'll say OLCL. And then of course, if it's above our A line, then it's just CL. So you can kind of see how all this is kind of working. So our default, we have our default class itself. So kind of like how we have GP, GW, SWSP, or ML in general, or OLML, depending if it's organic or not. I shouldn't exclude that. Then we have our middle ground, is what I like to call that, which is exactly what it is. Here it's a wash requirement between 5 to 12%. Here it's indicating, hey, if it's in the hatch area, it's going to be here. And even when it's even in the hatch zone for our gravel and our sands, it still follows the same thing. You'll have a combined or you'll have a dual symbol, combined symbol. You'll do what's called a dual symbol for that to indicate that it's not this or this, but it falls in between that. Okay, so you kind of get what's going on here. So it's only when you're dealing with clays, which is usually material that is that you have a liquid limit greater than 50. And remember, our liquid limit is just a moisture content. So in other words, it means 50% at 50% moisture or greater is where we were able to get our liquid limit. So if we have a high liquid limit, then it's just going to depend, which usually if it's a high liquid limit, it's either there is no hatch zone or low plastic index. It's going to be a high plastic index, high plastic index, and then it's just going to determine if it's going to be above or below our A line on that chart that I showed. And then it just comes down to, okay, is it organic or inorganic, and then depending on where it falls. So we have our OH, MH, which indicates, if it's organic or not, or is it CH, which just means that it's above the A line, and it's, people usually call CH as fatty clay. They usually call MH as lean clay. Usually MLCL is, well, sometimes they'll call CL lean clay as well, Actually, I shouldn't say that. Sometimes CL can be lean clay. It's just one of those things. It's up to the engineer depending on how they want to classify it, but it's all based on the data that you get. So this is how the unified classification system works. So every time we do a test and somebody wants to classify it in general, this is what we refer to all the time. All right, just let me get some tea here. And then we're going to move on to the AASHTO one. But I can tell you, I don't think this video is really going to be that long. I know there's a lot of talking. I know this is really boring, but I can't, it's going to be really straightforward when I demonstrate this. Okay, so now we have our AASHTO classification system. And as you can see, this classification system is greatly different than our unified, but it still pretty much follows the same premise. So, for our general classifications, it's asking, okay, we got to do a wash, right? Got to wash our material to figure it out. But here, unlike for the unified one, this one's saying 35. That's your magical number. Unlike for the unified, it was asking, okay, what's 50%? Or you have 50% passing or not? It's depending on where it's going to go. This one here is 35. So if we have 35% or less passing on the 200, then this whole section it's going to fall somewhere in this section. But if you have more than 35%, then it's going to fall somewhere in this section. Okay, so then we get into our group classifications. So this here is the same as what is going on down here, except for that they just have at the top. That's just their choice of doing that. So, whoop, didn't mean to bump into the mic there. So with the group classifications here, it's always going to be a 3. Actually, let me retract that. It's not always going to be a 3-digit value. So if we check out A1, you can't do this classification and just say, okay, I have an A1. No, it's either an A1A or an A1B. For A3, it can only be an A3. Doesn't have any additional information about that. An A2, it can't only be an A2. It has to be an A24, A25, A26, or A27. It has to be one of these to be coded as, for the classification system. So you can't say, hey, I have an A2 type soil. Well, A2 what? That's the kind of response you're going to get is an A24, A25, A26, A27. So these are your final, digits for that. So if we move on over here to our greater than 35% passing or 200 sieve, we have A4, A5, A6, and we do have A7, but if you do A7, it's either an A75 or an A76. So that's how this whole classification system works. It's a bit more simplified. But you have to do a lot more for an AASHTO classification than you would for a unified. An AASHTO classification, you're pretty much always doing a sieve analysis. This one you have to have the 10, the 40, and the 200, which the 200 you can get from washing it in general, but obviously, if you're going to wash it, you're going to determine your 200 by means of performing a sieve analysis in general. So there is no number 4 determination or anything like that. So that's the thing you got to keep in mind. So if we look into our A1 group, we have requirements for this to be within these groups, as you can see. So if we check out our A1A group, our number 10 sieve, we have to have 50% passing maximum. Okay, for our number 40, we have to have 30% maximum passing, and then for our number 200, it has to be 15% maximum passing for that to be part of the A1A group from our sieve analysis. Which I can tell you, it's heavily based more on the sieve analysis than what we're going to get for our Atterberg limits, which that's what this section is here. Because as we can see here, if we're in the A1 group, the only other requirement for to be in the A1 group is you must have a plastic, like your plastic index can't be any greater than 6. Which I can tell you, for this group here, if we look down to our usual types and significant constituent material, it's stone fragments, gravel, and sand. So we're talking, rocks. It really isn't going to have sand or anything like that. That's the reason why. That's the reason why you can see for the percent passing, 50% is your maximum that can pass. So if we think about the unified class system, how it's based on from your sand to gravel, how that was based on 50%, that's indicating that your number 10 sieve can't have any more than 50% passing, which if it's very, very rocky, you're probably only going to have like 20% passing or something, something along those lines. You're not going to have a lot passing because your number 10 is what's considered coarse sand at that point. Your number 40 is what's considered your medium sand, and you're not really going to get that in stone fragments and gravel. It's only including sand because you can have sand particles, or you can have finer rock particles included with your stone fragments and gravel. So, yeah. If we check out our A1B, obviously, as you see, it's getting a bit more looser now. So we can have 50% maximum on our number 40, but no more than 25% maximum passing the number 200 sieve. If we check out our A3 material, which is just fine sands, for one, it should be non-plastic. That's what NP stands for. And then from our sieve analysis, we need a minimum of 51% passing the number 40 sieve, and then no greater than 10% for your sand, for your 200 sieve. Jesus, sorry, I had a huge brain fart there. Okay, so now we get into our A2 material. So as you can see, our A2 material now, it's becoming more, this is what's more like, well, it's right down here, silty or clay, gravelly sand. So it can still be sand, it can still have a bigger consistency of sand, but as you can see, when it comes to finer coarse sand, there's no requirements for that. It's just, what makes it go into the A2 is if it has a maximum of 35% passing your number 200 sieve. But also keep in mind too, if we look at the variances here, if we look back at our gravel in general, we have 15 to 25% maximum. And then obviously if anything's over 35, then we start getting into our A4, A5, A6, A7 group. So the thing here is, it just depends on what kind of material you are going to have passing your sieves. You see here. So this is why here for like our number 40 sieve, as it's getting finer for our A1B here, it's finer, but we can have more material passing the 200 sieve, but nothing more than 25. But then here we can have a minute, or there must be a minimum of 51% passing your number 40 sieve, but nothing greater than 10. So really, kind of like how with this one here, or with our unified class system, how that indicated for, hey, depending on material or what's passing the sieves here, yeah, that's pretty clear cut and makes sense for the 200. But for the AASHTO, it makes it a bit more difficult. And even for myself, when I was trying to classify more things as AASHTO, which is something we have to do for FDOT, it's difficult because of this. So having a program that's able to do this is it's a game changer, and it's a lifesaver, because for FDOT they care about this, which makes sense, because if we go down to our general rating as subgrade, and remember, keep in mind, AASHTO is intended for roadway, so if you're talking about earthworks for roads, well, what makes up a road? Well, it's either asphalt or concrete, right? But what's below that? It's subgrade. It's soil, it's sand, it's stabilized. It's things like that, where here you can see for the rating system, if it's an A1 to A3 in this range here, it's considered excellent to good material to be used as a subgrade. But then if we get to our A4 to A7, that's fair to poor. And it really depends on what the intended use is going to be for. So if you have something that needs to handle a lot of drainage, let's say, you want something that can allow water to permeate or get through. If you have something with high fines, the water won't be able to get through as rapidly as something with lesser fines. So that's kind of the other reason why for the AASHTO classification system they have this hallmark right down here at the bottom to indicate that. So as you get into this region here of the table, so pretty much if it's anything that's greater than 35% passing your 200 sieve, okay, now you're hitting the fair to poor material, where now, okay, what is this going to be used for? Is this going to be general fill where, we're talking 30 feet below the roadway? Then okay, we may not have to worry about that. We may not have to worry about things like permeability. If you have a lot of water that's on the road that just needs to be dispersed, okay, then you can use that. So that's the other reason why they have that here, as unlike for the unified system, it doesn't say what's good or bad, because the unified system covers roadway and structures and buildings, and it covers a bigger, wider variety. Virtually anything that has to do with soil mechanics and general engineering that has to do with soils. Unlike for AASHTO, it focuses on roads. So, automatically drainage, usability and durability, things like that, and loads and yielding that's automatically in the forefront of everybody's mind, and they know that that's important. So since they know those are important factors, that's why this has that automatically, just calls it out. It doesn't mean that if it's a poor material that they won't use it. It just depends what the intended use is going to be. More than anything, if it's closer to the base of the road, or the stabilized subgrade, or more close to the subgrade levels, unlike for fill or embankment, you probably don't want to use this material, is all that's indicating, honestly. But despite all the extra steps that you have to do here, this is a lot easier to read and understand, unlike for the unified system here. Yes, there's a flow table, or flow table. It's a flow chart, absolutely. So you just follow. Okay, is it here, yes or no? That. Okay, it's this. But there's so much that it can be. That's the reason why that looks way more daunting than this here. This is only more difficult because there's so many different requirements, mostly with the sieves. I mean, granted, with the Atterbergs, it's the same thing, as well as we take a look here. So, as we get back to our A2, we already know if it's within 35%, but it's not going above 35 for our 200 wash. So for what's passing, okay. So it doesn't matter what other requirements that you have on your sieves at that point. If you have that, which really technically, if you have anything greater, if you're just doing sands with silt or silty sands or anything, if you have anything above 10%, it's going to be starting at least at an A24, depending on your Atterberg, and then it just gets more and more as you go. So you have your So this one covers your liquid limit and your plastic index. No matter what, if you do an Atterberg, you're still going to do your liquid limit and your plastic limits, but it doesn't care what your plastic limit's going to be. Okay. Thank you. Thank you, AVG. This looks like a good time for a sip of tea. Okay, so yeah, because this cares about where your liquid limit's going to be. This one doesn't care about what your liquid limit's going to be. All it cares, or no, what your plastic limit's going to be. You know, your plastic limit is just there to help determine what your plastic index is going to be. Because remember, it's your liquid limit minus your plastic limit is what gets you your plastic index. So as people will say, you know, LL minus PL equals PL. You know, if you're in any of those engineering classes with swell mechanics and whatnot. So as we look here, if it's if it's an A24 classification, we can only have a liquid limit no greater than 40 and a plastic index no greater than 10. But then as we get an A25, the minimum has to be a 41. So that means it's greater than 40. So that means it has to be a 41, but it can't get anything greater than a plastic index of 10. As you can see, it's kind of following the same premise as we go to A26 and A27. The only difference now is, you know, now it's indicating that your plastic index is greater than 10, but it needs to meet a minimum of at least 11. So as we head into our fair to poor materials, or our silty clay material, as it likes to say. So if, as you can see here, the requirement here, everything, whether it's an A4, A5, A6, A7, it has to be 36% or greater on your number 200 sieve. That's it. It don't matter whatever you get on the rest of your sieves, which I can tell you, usually if you're dealing with an A4 or greater, you're not going to have a lot of material on these other sieves. You know, there's not going to be a lot of sands. Is the true value of that. So if we take a look right back at our Atterberg limits and whatnot, as you can see, it's kind of repeating the same thing again, except for there's only one catch here when it comes to the A7. So when it comes to the A7 that's indicated here, it depends if your plastic index is less than or equal to 30. Then that's what's going to determine if it's an A75 or an A76. So remember, because the minimum is only 11 for our A7. So you have to have a minimum of 41 and a minimum of 11 for your A7 material, but it just depends, okay, what did you actually get for your liquid limit itself? Plastic index is equal to or less than your, oh yeah, equal to or less than your liquid limit. So in other words, if you have something along the lines of, which I'll try to demonstrate this too as we get into this. So if we have a plastic index equal to or less than, you know, for this example, it just says 30 and whatnot, like they both have to be 30 or less. Okay, so then that's what makes it an A75. If it's greater than your liquid limit, your plastic index, then that's what makes it into an A76. And obviously for this divide here, if you got an A4, A5, that's considered silty soils, and then A6, A7 is considered clay soils. And then there you go. That's it. That's the whole rundown of both the unified classification system and the AASHTO classification system. So now let's kind of get into it. I know we've already seen, like for example for B1 and whatnot. If we check out our unified classification system, we can see automatically, because we already have a sieve analysis, that we have nothing retained on our 3-inch sieve, 100% passing our number 4. We have 90.9% on our 200. We have a liquid limit of 43 and a plastic limit of 21. Our liquid limit oven dry is if it was organic, then you would do an oven dry liquid limit. And then, these calculated diameters come from the actual sieve analysis. I'm kind of surprised these didn't fill in, because we did input a sieve analysis. But as we can see, it's a CL. So if we look at our CL here, so it's above the A line, and our plastic limit is greater than 7. Good Lord, I hate that it's doing this. Yeah, no, it's just keeping it the same. I know, and I can't scroll down or nothing. Oh, whoops. Let me preview. Okay, there we go. That works too. So as we can see here, it's classified as a CL because we got our plastic limit and then our liquid limit and then our plastic index, which is our liquid limit minus our plastic limit, which gives us 22. That's 43 minus 21 gives us 22. So we have our liquid limit here, and then of course our plastic index is over here, so it's considered a CL or OL depending if it's organic or not, which this material that we use wasn't organic. So yeah, so it plots here, which makes it into a CL. As well as, remember we have material that's greater. We had 90% passing the 200 sieve, so it's more than 50%, and then it's just going down from there. We ran our liquid plastic limits. It was our liquid limit was less than 50, so it's on the low side, but it was above the A line, and our plastic index was greater than 7. So, what was our plastic index? It was 22. That's greater than 7, and there's our A line right there. Boom, CL. So hopefully you're understanding now the benefits of having a program that can auto-classify, because otherwise you would have to go through this for every single test that you do, which, don't get me wrong, you can get good with it, but I mean, if you have to classify 100 tests, in a day, it's going to take you a lot longer to reference this chart every single time to know, okay, what group does this fall in every single time. Now, will you get better at it over time? Yes. But is it a lot easier to utilize a computer to do it? Yes. As you can see, it calculated that for us, or it determined that for us, because that is the criteria that it has to follow. So now what I want to do, actually, let's check out AASHTO classification system here. So as we can see here, for what we have, this is saying this is an A76. So, let's check the work. Let's make sure if this is correct. So, we have nothing retained on our 3-inch sieve. We have 100% passing to number 10. We have 40% passing the or 40%. We have 95.1% passing to number 40 sieve. And then for our 200, we have 90.9% passing with a liquid limit of 43 and a plastic limit of 21. And then it asks, hey, is it a highly organic soil or not? So if we go back to our handy dandy chart again, which this one's going to be a lot easier to tell because there's not as many steps as we have to do for this one. So we know right off the bat we had 90% passing the 200. We're right here, so it's going to be within this group here. Anything above 36 is the minimum. We're above that, and then it's all based on our liquid and plastic limits. So our liquid limit, we had the minimum's 41, we had 47, and then our plastic index was 22, so it was over the minimum. That was A76. I kind of forgot. Yeah, so A76. So if we go back to here, okay, how's an A76? Well, your plastic index needs to be greater than your liquid limit. Plastic index greater than your liquid limit. Hold on, I'm having a brain fart right now. I just want to make sure if this is actually doing this right. So if your plastic index is greater than your liquid limit, so for this example 30, the soil is A76. So in other words, your plastic limit is less than. Oh yeah. No. That's right. Okay, yeah. So your plastic index is greater than your liquid limit. But then why is it indicating your plastic limit? Because that's your PI. So your PI is greater than your LL. Then the soil is A76. But if your PI is equal to or less than your LL, the soil is A75. It's saying A76. Yeah, because our PI is 22. Oh yeah, that's right. If it's organic, it's A8. I forgot about that part. It just becomes A8. So if you have anything greater than 50% for your organic content, that's weird. That doesn't really seem right now if we follow that chart, unless there's just something I am not understanding here. I know. I wonder if it's going to hit me like later in the video, and I'm going to be like, oh yeah, that is right. Or oh no, because it's saying it's an A76, but you can only pick an A76 if your plastic index is greater than your liquid limit. But our liquid limit is it's 40. It's like 42, 43. And our plastic index is only 22 because it's 43 minus 21. So our plastic index would be 22. So why is it? I'm not too sure why it's doing that. That's very weird. I mean, this is an older version, but then again, I mean, unless this is an older version of the spec, I don't know. It's hard to tell because that seems contradictory to me. Because if your plastic index is greater than, so remember, plastic index is 22. So if your plastic index is greater than your liquid limit, which is 42, and it's not, then saying the soil is A76. But then why is it giving an example as if, is this worded wrong? Should this be plastic limit? Nah, it can't be plastic limit because if your plastic limit is equal to or less than, well, if it's equal to in general, then the thing is then your value is going to be 0 for your plastic index. If your plastic index is going to be 0, it can't plot, which means it's non-plastic. Which I'll try to demonstrate something like that too, as well, because that's very possible. Huh? That's weird. It's very, very weird. I don't know. I don't think that's 100% correct, but I don't know. Maybe, I mean, it is very, very, very early in the morning too for me doing this. So maybe I'm just not as sharp as I am, or maybe I'm too reliant on computers. That's a good point. Good chance of that too. Okay, so we're going to make a new test here. And for this new test, we're just going to put in a we're just going to do a sieve analysis. So let's just say 249. Everything else is kind of whatever, and I'm wondering if, and for this one, for this example, nothing, no Atterberg limits was done, so we can just say it's non-plastic. Yeah, I don't need a specification set. All right, so let's continue. And we'll just use this or something. Oh yeah, they ain't gonna let me do that or that. Okay, I think I'm actually going to have to type in values. It's not going to let me do anything, is it? Yeah, no crap, it's an invalid number. Because everything's 0. Okay, yeah, no, I think I'm actually going to enter in values. I was planning on just entering into percent finer. I don't know, actually, let me just, oh no. Yeah, I'm actually going to have to enter it in. I was wondering if I could just enter in the percent finer and whatnot, but it ain't going to let me do any of that. Of course not. It's an older system. So let's see here. So 18025.90. What do we got? 16923.1 and 0. And then there's no split. Okay. So let me just make sure I got all the sieves. So that one 1 3/4, ½ inch, 3/8, 4, 8, 10, 16, 30. What the hell? 30, 40, number 40, number 50, number 100, and then number 200. Alright, so let's enter all this stuff in. Let's see, 14.00, 66.60, 86, 83.40, 11.40.60, 13, 4.40, 14.0, 25.10, 10.0, 15.855.90, 16.109.30, 16.132.80, 16.517.0, 1600.6. Okay, there we go. All right, let's take a look at the curve. Okay, so if we look at this curve here for what was entered in, this is technically what's called a well-graded curve. So this is as you get a gradual slope, it's called well-graded. When it's poorly graded is when it just drops. So if we are to look at B1 again, and then our grain size distribution, well, that one's not really a good one either, but this one just sharply drops as well. Unlike the other one, how it just gradually goes down, this one's just kind of, so actually it is two other ways. So you can either have a sharp drop where it would kind of start here and then just go down and then over to your 200, or you can have something short like this as well that can mess with that. I wonder if it's not going to classify the other one because I think it did say it needed to be blank, right? Or I wonder if I gotta go to Atterberg limits. Oh, good lord, this is what I hate. Like, I can't access everything. Oh, whoops, I didn't mean to do that. I meant to do that. Oh, good lord, okay, let's... Oh, jeez, I'm just gonna have to mess with everything. I can already see this happening. What's seamless mode? Oh, where everything's down here. I don't know, that don't seem to still work too well. Yeah, full screen mode kind of sucks too. It's just not including everything, and I don't understand why this thing has to be like this. Okay, it just says adjust window size, and that don't do nothing. God, I don't need it to scale. Oh, good Lord. I don't know. Let's try 1280 by 720. Oh God, no. That's a. Oof. God, this is horrible. I don't know why. Oop, I'm typing C's now into water content. That's supposed to be a number. Yeah, that just takes us to the grain size. That's very weird. I wonder if everything's supposed to be a blank. God, yeah, no, that's a nightmare. Good Lord, I'm making this into a fucking shit show at this point. Yeah, I don't think it's going to classify. Well, I guess I have to put it here. Wow, it's saying GPGM. That's crazy. Zero point 0.0, that. Yeah, I don't think it's. Wow, GPGM. Interesting. It's still considering that being poorly graded. Huh. As an A1A, which makes sense. Wow, that's wild. You know, I mean 6.8, which makes sense. Um, it's predominantly, even though we have. Oh yeah, never mind. That's what's less than a number 4. Okay, yeah. So that's your percent passing. So 35.9, right? Yeah, 35.9. That's your percent passing. So that means you have material that's greater. You have 50% or greater, which that's what makes it into the GP classification. It's only GPGM because of the wash. But that's weird because this is technically well graded and it's classifying as GPGM. But I'm guessing it's probably because of these values, which, let me double check that real quick. Yeah, 12.8 for the D60. Let's see, the D30, 3.43. Yeah, that's right. Okay, you know what? I think I know why this was, because technically the example that I used had a hydrometer with it, and that's probably what made it well graded. Yeah, because that D10 is not right at all. But that's weird too, because I thought the D10 was dependent upon your number 10 sieve. Yeah. Yeah, actually. I want to view this report real quick. I'm very curious. It's okay. See, now everything's beginning to classify out. No, not Can I view? Where the fuck's my preview? Here we go. Oh wow, that's weird. None of these values are filled in. Oh, because I'm looking at the wrong report. I grabbed the wrong one. Shit. That's not what I wanted. Yeah. Okay, I was about ready to say, what the hell is going on here? No test has been selected for printing. Yeah, I did. I selected 249. Oh, I guess I had to select that. Good lord. Oh, good lord. So many different things you had to do back then. You know, the newer versions is just a button you press and boom, it prints. So I just. Man, I guess it's because. Maybe because this had a hydrometer performed. Damn, there's not even a D90 here. So we got a D85, 22.8, that's right. D60, 12.8, that's right. D50, 8.8.6. That's a little off. That's a little off because we got 8.8.4. D30 is 3.43. Could be 3.44 if you, depending on rounding. Because the later versions of Geosystems, it's stupid accurate. D15. Wait a minute. Ooh, yeah, that D15's off. It should be 1.30. So it's somewhere around here. Actually, yeah, what is this CC, CU? So CU is, yeah, here I got 49. This is 23.82, and then the CC should be 1.71. But I think the only reason why, because this had a hydrometer with it, which probably is what made it get up to well graded. I mean, don't get me wrong, the hydrometer doesn't look great because there's really no, silts or particles to make the hydrometer float, so it just kind of just drags on the ground. But as we can see here with the report, we have 64.1% gravel, which makes it into the G classification. And then it just depends on the silt. We had 6.8, so it made it greater than 5, so that's what made it GPGM. P indicating that it's poorly graded, which this isn't really poorly graded. That's a pretty nice curve. I mean, poorly graded, it's like I said, it'll just drop and then kind of finish out. It's a steep drop. This is kind of a gradual drop. It ain't a perfect gradual drop because a lot more is kind of like, it's not like a straight line, but it's almost like a straight line. But it isn't all the time. Damn, well, I thought I had a good example, but I guess not. I know. But, I mean, this is an A1A, which totally makes sense why it's an A1A. Because if we... Oh, God, everything is all messed up. Good Lord. Lord have mercy. So, all right. So this is saying this is an A1A, which more than likely makes sense because if we check out our sieve analysis, our number 10, we had 22.2% passing. The maximum is 50% passing. So we have not a lot passing, which makes it even more coarse. Our number 40 sieve is 9.0%, so the maximum is 30, so it's less than 30. And then of course for 200 it's 6.8, right? Yeah, 6 or 4.4. Never mind, it is 6 point something. This is only saying 4.4 because of I'm wondering if I'm messing up. I mean, it's still going to be an A1A, but now, I'm wondering if I messed up the gradation while entering in the data, mechanical data. I mean, that is technically our afterwash. It's just, is this doing something weird? Should this be 0? I think I'm going to get an error. Okay, how did that change it? That made it like 4%? No, it's still 6.8. Yeah, huh. That's really weird. That is really, really, really weird. God, all these extra steps. Golly, I feel for those people that had to use this back in the day. Good Lord. I mean, yeah, it makes it a lot easier than, I mean, either building an Excel table or, actually hand plotting out the curve and stuff. But good night, that's a lot of extra steps to be doing just to print something. Oh my goodness, I'm glad they simplified that. I'm pretty sure that was probably their number one complaint. Can't believe it's poor, but I mean, it's like I said, I should stop saying that because technically this was treated as a hydrometer, technically, even though it was like an inch and a half rock, but they wanted to do a hydrometer on it because they wanted to, I guess. Usually you don't do that. Cool. Okay, so I don't know. I think you guys get the gist. I think I bored you guys enough. I was thinking about adding some additional things so you guys can see the classes change and whatnot. But I think you guys get the gist for how classifications work. And if not, then you guys are sleeping really really hard because I have the best bedtime stories. What can I say? Yeah, but I think that's pretty good for the subject matter that I covered. I know I can add more examples, but I mean, you guys seen the table. That's how it works in the end. So I don't I think I feel like I'm beating a dead horse at this point. So yeah, so that's classifying soils. That soil classification. That's not what I wanted to do. Yeah, so that's soil classification. So, yeah, if you made it to the end of the video, cool. I mean, granted, the past few times I have streamed this and whatnot, I didn't really have an audience, so I don't feel too bad not being able to stream this. Just because I haven't really gotten any kind of interaction or whatnot. But I'm hoping the next one I'll be able to or whatnot. Um, I know there was an update for Telegram. I'm assuming there's probably a bug on it, and they probably gotta fix it. And maybe next time when I do this, I won't run into this problem. But obviously, if I can't stream it, I can't stream it. But anyways, yeah. Hopefully you guys enjoyed this. If you made it to the end of the video, cool. Hopefully I can still continue to stream these. But I do stream them on my Telegram channel. If you want to join and fall asleep faster before this video comes out, I guess, or if you're interested, I don't mind answering any questions in the comments below. Yeah, I don't know what else to say. I mean, this is my everyday job. It's fun, right? Fun for some, maybe not for all. But yeah, I hope you guys enjoyed, and I'll catch you in the next video. See ya.